Hello, everyone. So yeah, I'm Javier, and I'm joined today by Jay. We both work on production engineering, and we are based in the London office, Meta's London office. Today's topic is going to be experimenting with AI-driven systems. All right, picture this. It's Friday night. You're out in your favorite restaurant, and it's been a very long week. The only catch is that you're on call at night. Now, the moment the food gets to the table, you can feel it in your pocket. You can hear it. Sounds familiar? Well, dinner is ruined and something is very broken at work. That was me and definitely Jay, even more so, not long ago. So tonight we're going to be talking about what was causing these late night incidents and how do we get over time to a place where we can, most of the time, enjoy our weekends again and late night dinners. So the agenda for today is going to be starting with a bit of an introduction about experimentation in general, and we will illustrate with some examples at Meta, specifically on the ad systems, that is the ones that Jay and myself work on. Then we will move on to explaining a bit more about what happens when experimentation becomes the default in production, which is the case in these systems, actually. Like, most of production is being served now by experiments, and most of the user traffic goes to experiments. When this is the case, you can imagine everything's in constant change, and that provides quite a lot of fun on the live infrastructure. Then we will move on to how we actually tackle the problem with the SRE mindset, production engineering, to this problem that we called experiment safety. And finally, we will finalize today with some lessons and learnings that we hope you can apply as well, outside of Meta in a smaller scale as well. So let's start by talking a little bit about how we use experimentation at Meta inside of the ad systems. And to illustrate this example, I'm going to start with showing you something we all love, right? And we have seen very often, which is an ad that you can find maybe on Facebook or on Instagram. So when you see an ad like this one, what is actually happening behind the scenes? What's happening is that the Meta systems are trying to match from millions of ads that are on the inventory, which one would be the best match for you at a given point in time. To do so, there are some advertiser constraints that are received by the actual advertiser. They might want to target a certain audience in a location, in a certain age group, and then Meta takes these inputs and then joins them with a lot of information that Meta contains as well about what ads perform better in a given time and what outcomes the ad is trying to achieve. And then a lot of machine learning models are actually running behind the scenes here, and cutting-edge AI that is being designed to actually try to optimize for the advertiser, the outcome, and also for the user experience as well. So it's a fine balance to have in these systems. Now, just giving the context of what the ad system is doing behind the scenes brings into experimentation. So if you're an engineer working on these systems that have so many machine learning models, and you're trying to optimize the predictions that are happening, how would you actually go about it? There is not an easy way to test these things on production, whether the change is actually positive or negative overall. So that's where experimentation comes into place. And I will give you just one example of one experiment in case you're not familiar with these kind of systems. How does it look like? A single experiment. So for any given experiment, there will be at least two versions, usually. In the image, you can see version A will be the ones that is, we call it the control version, which is the one that is basically the current behavior in production today. And then version B will be the test version, which is the one where you apply the change you want to actually test in production, which probably is like a machine learning prediction change that you hope is going to be a positive change. Now, this system is an online A/B system, which means that real user requests are actually going to your experiment. It's going to be going to your experiment. We use a platform internally at Meta, but outside you can find as well services that use for experimentation that you can apply on your day-to-day as well. And what this system is doing is, for all the user traffic, it's going to split it in two halves, and then some users will go to version A, some users will go to version B, and these two sets of users will never overlap. So during a period of time, each of the versions will receive the user traffic, and you will be able to collect the data that you want to collect there in order to then apply some statistics and get an insight of whether the change is actually positive or it's actually a negative change. And this happens all in real time in production. Now, this is just one experiment setup that one engineer might be doing. And to get a sense of the scale here we are talking about in the case of Meta, for the ad system, there might be around 1,000 concurrent experiments that are running in any given point in time. And those are being run by thousands of engineers that are distributed globally. that work in different teams that have different objectives and are basically testing a lot of different logic all over the place. So that brings a lot of fun to our production environment, as you can imagine.
Cool. So now you have some understanding of this domain. Let's talk about the challenges that are presented when experimentation becomes almost the default mode of operation, and how we as reliability-focused engineers are able to handle this kind of ever-changing system and its resultant behavior. So let's start with a kind of more concrete overview of the system architecture. So you can think of ads as being kind of a big funnel, and the goal is taking these millions of possible ad candidates and reducing them down into kind of a handful that will eventually be shown to the user, all in kind of sub-second latency. And this process is broken down roughly into 3 components. The first of these is kind of a retrieval stage, and this is where we're fetching all of the possible ad candidates from our library, and we're using a combination of different techniques here, but mostly on the ML side, and we're, this is flashing, and then we're quickly identifying the ads that a given user is eligible for. So for example, if we're determining the ads for a user in Dublin, then we can probably exclude ads for a user based in Paris or London or other places like that. Cool. So once we've got this kind of retrieved set of ads that the user is eligible for, we then perform some ranking of these ads using our more advanced ML models. Now, the goal of these models is to produce a value, and this predicts the action rate of the user. And so that is the probability that showing this ad to a user will lead to some desired outcome for the advertiser. So you can think of this as like visiting a website or downloading their app. And so we order this list of ads by their predicted action rate. And then this gives us kind of the most suitable ads for a given user, given this set of inputs. And so once we've got this ordered list of ads, we then run them through the auction process. And this is similar to how an auction works in kind of the real world. And we determine the winner based on, firstly, how much the advertiser is willing to pay, but also the kind of estimated action rates that we calculated, and also the some understanding of the ads quality. And so this kind of removes any spam or clickbaity ads from the system. And so at this point, we've got the final set of ads that we then return to the client, and then we merge with the rest of the posts that will eventually be shown on the feed or in Reels or Stories. Now, the process doesn't stop there. Up until now, we've kind of been blindly testing these, using these models' predictions of the estimated action rate without understanding if they're actually any good. And so what we end up doing is calibrating these predictions with the real world. And this tells us whether the system is behaving as expected or not. And so the way we do this is by leveraging a set of feedback loops that gradually adjust the behavior of the system over time, depending on how good the predictions are. So to give you an example, if a model predicts that a user will click on an ad in 50% of cases, but we only see a kind of 10% click-through rate, then it's likely that the model is not very accurate and so needs recalibrating to reflect the real world. Now, if we all put our reliability hats on, we see that this self-improving approach, well, is probably going to lead to better business outcomes. It suddenly makes it much harder to determine if the system is acting as expected. Cool. So now you hopefully have an overview of the system. So how do engineers actually go about testing this potential improvement using the A/B testing process that Javier described? Well, first they head to our experiment UI, which allows them to define their experiment with some basic metadata, like a name and a description, and size of each of the user groups. And the output of this tool is a kind of unique experiment ID, which then plugs into our pretty high-level API, and this is used to gate different code paths in our overall business logic. Now, this can sit in any one of the 3 steps that we talked about before, ranking, retrieval, and the auction, and it's pretty flexible, right? The engineer is free to do whatever they want within these blocks. They could change the model that gets invoked. They could switch out to a different sorting algorithm, kind of whatever makes the most sense for their use case. Now, I'm sure you've already started thinking about this, but you can imagine a lot of things going wrong when you give this much freedom to engineers. And so let's walk through an example of what could actually go wrong here. So suppose there's an engineer wanted to make a change to an ML model used in our ranking stage, and I'm one of the users involved in the experiment. So right now when I open my Instagram feed, the existing model is predicting that I want to see some ads for a new console game that's coming out next week. Now, this fits pretty well with my interests, so I'm tempted to pre-order it, and it seems like an overall good fit. So the engineer that wants to validate a new model that they've been working on, and this is going to reduce overall memory usage in the system. So they go and update the configuration file that changes the ranking to use this new model for any users involved in the experiment. Now, when we deploy the model, we realize it starts to produce some inaccurate predictions. And so for me as a user, instead of getting ads that I was interested in, I start getting some ads for some, I don't know, new gardening equipment or something, which doesn't sound like exactly what I had in mind after a hard day at the office. And so it begins the process again of investigating this issue, once again interrupting Javier's dinner, and us needing to figure out what exactly went wrong. And so, as we kind of alluded to earlier, there's not just one model involved here. There are many different models involved in this selection process, and each one plays a very different role in the kind of retrieval and ranking of these set of ads. And so, while one of the requests might be served by this set of models, another request might be served by a completely different set. And so it's really this sprawling set of code, configuration, and model changes that make up an experiment that make it particularly hard to root cause exactly what's going wrong when we detect these kind of user engagement regressions. So after fighting several of these incidents and interrupting many of our evening dinners, we kind of took a step back and looked at the incidents a little bit more holistically, and rather than just kind of focusing on some small tactical fixes after each one. And so in that analysis, we found that experiments on our side typically failed in one of three ways. The first of these, as we've described, was really around model mispredictions. And so this is where the system is kind of acting as expected. We see availability remaining high, system resource utilization looking kind of fairly normal, but just the predictions are completely misrepresentative of what's happening in the real world. The next one is where we saw infrastructure outages caused by experiments. And this is kind of your more traditional kind of issue that you might typically seeing, like crashes or out-of-memory issues. And the final one was actually experimentation infrastructure itself. And in particular, since every request would go through this experiment allocation flow, if this component starts throwing errors or incorrectly computing the allocation, then we have the potential to directly impact the entire request.
Yeah, and having experimentation as default brings as well some business and people challenges, of course. Not all is technical. So on the one hand, you are experimenting here with critical infrastructure systems, right? So when you allow everybody to test on production and be so flexible, when a system is generating billions of revenue per year, or there are billions of users actually accessing those services, you can imagine that it's pretty sensitive, right? A bad experiment can actually cause real impact to the business, which it happens sometimes. And on the other hand, you have all the internal engineers that now rely on experimentation on their day-to-day work. They want the most flexible system, they want to move really fast, and they want a lot of flexibility on production. So that creates a lot of tension between the business side and then engineers that want to move really fast. And then the other challenge we saw once there is so much experimentation happening is that experimentation systems usually are a thin layer on top of the existing infrastructure. And then every experiment is usually run by different teams, different organizations, and people that care mostly about their individual experiment, their goals, and not about the overall system and reliability. So what happened here is that then it was hard to pinpoint who should own reliability as a whole, for each experiment, for the infrastructure. It was not very clear. And that was a good opportunity for production engineering and our team to take on that challenge and own it end-to-end in a horizontal manner.
Great. So hopefully you roughly understand the kind of problem space that we're talking about at the moment. So now we're going to discuss a little bit more about how we were able to solve this. So as Javier alluded to, in kind of early 2022, we spun up a new experiment safety initiative that was led by our production engineering team. Now, within this initiative, we set up several investment areas, some of which may seem fairly familiar and should be broadly applicable to things you focus on as you tackle reliability issues within your own products and services. In particular, we kind of considered the type of issues that we'd seen experiments create, and then figure out how we could identify these as early as possible in the experiment lifecycle. And so this led us to four main investments. The first of these was really around change safety and isolation, ensuring that as we deploy and roll out experiments, we could do this in a safe and predictable way. And so this is similar to how we've expected code rollouts to work kind of over time. The next one is really around monitoring and observability. And this was ensuring that every experiment had the necessary monitoring to capture how it was performing over time, irrespective of which service it was modifying or the configuration that it was updating, without needing the individual experimenter to do additional work. The third of these was around mitigation. And one thing we'd learned is that it became pretty hard to predict exactly where the next issue was going to come from, especially in this kind of ever-evolving system. And so we wanted some kind of guardrail that was available that we could use irrespective of when something went wrong. We could quickly stop that experiment and prevent it from causing further issues. And finally, as Javi discussed, not everything can easily be solved through just technical problems at all. And so it was often about instilling these cultural changes through new processes in addition to these kind of technical improvements to properly solve the problem. Cool, so let's talk a little bit more about these themes in detail, and starting with change safety. So as I mentioned, our strategy in this area was to really shift left the identification of this problem as early as possible in the experiment lifecycle. And so it was really important to do this before it even touched production at all, if we could. However, when we started this, experiments did not go through a structured workflow as they went in and out of production, and this really limited our opportunities to build observability and guardrails. And so the first part of our investment was actually to define these kind of concrete experiment states that it could be in, and then integrate these with a workflow engine that was able to transition experiments through this structured set of steps as it kind of progressed throughout its life. And this state machine actually ended up becoming the kind of centralized coordinator between experimentation and the rest of the external systems that we relied upon. So now we have this kind of structured workflow. Let's walk through an example of an ML experiment's lifecycle and maybe talk about the different guardrails we were able to put in place. So as I mentioned, the kind of first guardrail we implemented was before an experiment even started. And in particular for our ML experiments, we were able to generalize them enough such that they could be configured without needing to write any code or update a configuration file. Instead, we would capture the relevant inputs through kind of a fairly simple user interface and take in some basic parameters like the model ID and the type of model you're updating, and then use this to generate the code and configuration changes on behalf of the experimenter. Now, this actually meant we could perform the process of kind of deploying the model into production and ensuring it was correctly scaled before it received any traffic. But it also gave us the opportunity to implement some pretty basic sanity checks, like checking the model ID actually existed and was supposed to be used for the purpose you're intending it to be used for. Now, before we get to kind of any online validations, we were then able to leverage kind of a set of offline tests after the experiment has been defined to validate a set of metrics to determine the model's kind of suitability before it touches production. Now, these tests were introduced based on some repeated patterns shown in our incident analysis of how ML models typically failed in production. And failure in any of these tests would block an experiment from proceeding any further in its lifecycle and require some investigation from the experimenter, similar to kind of how a CI system would work for code. Now, this solution actually ended up blocking hundreds of experiments in the first 6 months alone and saved us kind of multiple costly investigations, as well as making it much easier to isolate the problematic experiment rather than being in production with all the other models using at the given time. So let's dive into some of these validations in a bit more detail. So the first of these was kind of our offline inference validation system. And here we kind of deploy the model in an offline testing environment, which mimics the production setup as closely as possible. We then simulate several requests using our labeled training data, and then analyze these predictions generated by the model in the response. Now, since we're talking about experimentation, the models are often an improvement from an existing baseline model, and so we use that baseline as a way to set an expectation for how the new model should perform. If the new experimental model deviated too far from this baseline, then it was likely that something had actually gone wrong in the training or setup process, and so the model wasn't going to perform well when exposed to online traffic. In particular, the metric we were interested in here is called normalized entropy, which is a measure of how effective the trained model is at predicting a given outcome, normalized against the training data set. So then, assuming the model performed well in these kind of offline inference tests, we then perform this round of resource usage estimation. And one of the biggest constraining factors we see in the number of experiments that we can run concurrently is the physical resources we have in our data centers, so GPUs, memory, things like that. Now, this resource estimation enables us to understand the cost of these models before we deploy them in production. And we do this by running a load test against them using the same kind of offline testing tier by gradually increasing the request load over time without allowing for any auto-scaling to kick in. And this allows us to determine the point at which the error rate from the model breaches our acceptable threshold. And at this point, we can then take this data plus a kind of quota management system we use to determine whether we allow the experiment to continue or whether we should block it until more resources are freed up. Cool, so assuming everything goes to plan and our experiment passes these kind of offline checks, we then proceed to move the experiment to the next stage of its life cycle, which we refer to as the canary. And this is where we enable the experiment on some subset of production traffic, still within an isolated environment, so in this case, in a single data center region. Now, this doesn't give us any statistically significant experiment results, and we can't use it to make decisions, but we can perform a pretty standard smoke test to validate the end-to-end selection flow works as expected, and there aren't any regressions in kind of key business metrics, as well as our system resource utilization. Now, we bake experiments in this state for a few hours until we determine that we've got good signal that all of the resources have been loaded, request and response rates look good, and we don't see any regression on our top-line kind of metrics. And now at this point, we've kind of collected enough data points, both offline and online, and we can actually make a decision about whether the experiment should start in full. Now, historically, we made this as kind of a binary decision. We made sure that every experiment met the criteria that we set out before. It passed every single check and became this kind of very rigid guidelines that required us to meet before an experiment could be shipped. Now, as you can imagine, as soon as these checks became noisy or flaky, then this would not only create significant operational load for the maintaining team, but it would slow down engineers from making progress, and they'd have to be manually unblocked. And so to solve this, we're able to leverage a risk score concept that was being developed at Meta at the time, and this determined what should or shouldn't ultimately be released in production. And so the way this works is it leverages a set of heuristics about the experiment from the online and offline tests, and this makes a decision about how risky it would be to put it in production and the likelihood of it causing an issue based on some historical data. And so this risk concept also meant that we could adjust our risk tolerance depending on external factors. So if everyone is online and working, we can kind of allow increased risk tolerance. And then during the weekend or during holidays, we can then all enjoy our downtime in peace because we decrease our risk threshold. And so this actually enabled our engineers to move much faster. And one of the biggest pain points and complaints we received was all of these guardrails we'd introduced. And so this gives us a balanced approach between risk and allowing everyone to move fast. And there's a link here to the paper if you're interested. Great, so once the risk profile has kind of been evaluated, and then the rollout is allowed to proceed. So we followed a fairly standard rollout process, introducing the experiments into more and more regions gradually, gradually throughout time, and then introducing some health checks in between each of these phases to make sure that the rollout proceeded as expected. Cool, so just because we rolled out the experiment successfully doesn't really mean that it will continue to be successful. And in particular, since the system is so dynamic with these kind of feedback loops constantly adjusting the behavior of the system, it was really important not just to do the rollout safely, but to continue to monitor experiments throughout their entire lifetime. So to do this, we had to develop an experiment monitoring framework where each experiment is automatically onboarded rather than requiring engineers to do additional work upfront. And so since every experiment is different in nature, some might be changing a retrieval model, some are changing how we index data, we needed to really think about the metrics we would use to monitor each of these experiments. And this is where we settled on kind of the business metrics that would really capture the outcome of an experiment rather than exactly the behavior the experiment was changing. And so we had several metrics that would make sense here. Most of these were really around the number of impressions that was being seen by users, as well as the number of clicks and conversions, as well as the overall average cost per ad. And so if we see any of these regress in either direction, then we were able to kind of fire an alert and involve the experiment owner. And so we were able to build these kind of per experiment breakdowns into our core ads events logging services, and we were able to capture these for every experiment by default. And so if an experiment, for example, is targeting 5% random sample of the population, then it would make sense for that experiment to also occupy roughly around 5% of global ad impressions. And so we could actually measure this metric to pretty fine confidence intervals. And so when something does go wrong, as it always does, then it was easy to identify which experiment was actually causing the issue, and based on monitoring and alerting that we set up on these two different time series of the actual experiment behavior and the expected behavior given the global value. Now, while these business metrics act as a pretty good catch-all for kind of determining if there's an issue somewhere with an experiment, it doesn't really tell us why there is an issue or what's actually going wrong. Now, more often than not, we found that the issue actually stemmed from model mispredictions. And this is where there's kind of some change in the estimated action rate determined by a model. So let's take an example. Here we have the kind of predictions produced by one of our existing production models, and it follows a fairly standard distribution where the predictions are on the x-axis and the frequency is on the y. Now, if we do the same for an experimental model, we should expect to see a fairly similar distribution. But if instead we see something wildly different, like a significantly shifted mean or a much smaller variance, then it suggests that there's probably something wrong with this production model. And more concretely, we use the Jensen-Shannon divergence to continuously compute the difference between these two distributions in production, and then allow us to create alerts when these two distributions diverge too much. Now, there's definitely some art to this science, since experiments are, by definition, expected to introduce some change into the system, so you don't expect the two distributions to align perfectly. And so we allow for some tolerance in kind of the deviation between these two values. Great. So now we have all of our kind of preventative and observability guardrails in place. We still need some way of quickly stopping things if they do go wrong. Now, the first of these was an extension to the workflow engine that we talked about before. And this was actually able to trigger the process of stopping experiments automatically if one of the issues were detected in the business metric alerts. Now, this is pretty effective, but it doesn't go down too well if your system suddenly starts stopping all experiments because of some false positive or data logging issue. And so we actually evolved this approach to include additional mitigation steps. And one of these was actually including an automated LLM-driven debugging step. And so we would give the LLM context about the experiment using the key metric data as well as monitoring and metrics that were available about the experiment. And this would then generate several hypotheses of issues that could be going on with the model or the experiment. And the experiment owner could then manually investigate these before their experiment would get stopped. So again, this was kind of balancing that developer productivity with reliability angle. And of course, not everything goes to plan, especially where AI and ML is involved. And so we had our trusty last resort, the kind of big red button that would stop an experiment immediately and force all of our user requests to go back into that default system behavior.
Cool. And of course, not everything is technical solutions, even though they are the best ones, usually. But we had to implement as well some people and process changes as well. So for completion, I will cover those. The first thing we did was fixing the accountability and ownership issue. If you run an infrastructure, experimentation infrastructure like this one, as I mentioned before, you might see that it's a bit difficult to find the ownership of who owns the reliability side. So what we did here is we assigned one person, in this case, Jay, to be the tech lead for the whole space, caring about experiments or the infrastructure, and making sure we had very comprehensive plans in place. Secondly, we collaborated heavily across teams, since, again, the different failure scenarios that Jay described before had different solutions. The infrastructure could fail, or an individual experiment could have bad predictions. That required different approaches and different roadmaps to be done with different teams. And finally, we had to do a lot of methodical analysis here, since at the beginning of the journey, the data was very sparse. We didn't have a lot of information about what experiments were failing, what was the impact of each failure, and what was, root cause areas, teams, etc. So first thing we did was collecting all this metadata for every incident, and that really informed all the rest of the work over time. And that leads me to some of the lessons and learnings that we had during this journey, with the first one being to solve a complex reliability problem like this one is, using data-driven insights is very powerful. At Meta, we use a lot of data all over the place, and reliability issues we also do very much. So as I mentioned before, at the beginning of the journey, there was not much data to be analyzed at the very beginning. So what we did is, after collecting all the metadata through every incident, we were able to build dashboards that became our reference for real-time, what were the incidents that were happening, what were the root causes, and then break down the problem in really clear areas. Once that was done, we were able to then create plans that were targeting each of the individual spaces with different people, different roadmaps, and then see over time the evolution of each of the areas, and be able to basically see if the improvement was being done in the right direction, and if any regression was happening as well. Second lesson that we saw is that you will find as well is when you focus very heavily on reliability, you might be impacting negatively developer velocity. And that's something we saw ourselves. We leaned very heavily at the beginning on reliability in our projects, and then we got complaints from some developers saying, hey, we are slowing down my day-to-day. And so we had to find some trade-offs here. So the advice here is when you work on a topic like this one, be very data-driven on reliability and measure the impact, but also be data-driven on the developer velocity. If you can have a metric that captures the throughput or the way the engineers are putting changes into production, and be able to monitor this metric as well, you will be able to see if there is any regression when you're working on reliability on their actual day-to-day work. And when you're thinking about implementing more and more reliability guardrails, you can then take a decision whether it's actually worth doing based on the risk, or actually it's better to let engineers move a bit faster. Oops. And then the final lesson that might sound obvious, but is the importance of high-quality monitoring and then implementing over time earlier guardrails. So in our case, the key part was when we had monitoring for each individual experiment on production, and we were able to monitor both the business metrics and the system metrics for each experiment. Then we were confident that if everything went wrong in production, at least we had some guardrail that would alert the experimenter and also stop automatically the experiments if it was a really bad, a very bad change. And once we had that safety in place, we were able over time to then shift left and then implement the guardrails earlier in the life cycle of the experiment and make sure that the issues were not happening on actual production, which was in most cases too late. So indeed, we were able to enjoy again our weekends and dinners after all this work. And that's it for today.